Okay, so back here on slide 34, now that we've got MM1 constructed, we're going to construct M1, which is a map from char to int, from the pairs contained within MM1. Now the map from char to int is still using char as the key, but this time multiple copies of the same key will not be allowed. And when we display the elements of M1, as we're doing here on slide 35, what we're going to see when we look at our first possible duplicate key, the L, notice that the first pair in which the key is an L, that is L3, is stored in M1, but then any subsequent pairs that have a key of L are rejected. Those are simply not stored into the map M1. So the pair L4 is rejected, the pair L1 is rejected. And so all we have in M1 is the first occurrence of the key L with its value 3. Likewise for O, we have the first occurrence of the key O with its value 5, and we see that in the output, but the second occurrence of O with value 9 is rejected. Alright, well, let me clean up my highlighting here on slide 34. So we have constructed M1 using the pairs taken from MM1, the multimap, from the beginning element up to but not including the end element of MM1. We now do the same thing to construct our unordered multimap from char to int, using the values from MM1 begin up to but not including MM1.end. For the unordered multimap, the keys are in some seemingly random order, but duplicate keys are allowed. So on my system, when I run this, I happen to get key W value 8 as the first thing displayed. Then I get key O value 9 displayed, followed by key O value 5. Notice here that key O value 5 actually comes ahead of key O value 9 in the multimap MM1, but when we construct the unordered multimap UMM1 from MM1 and display the unordered multimap, the values come out in the reverse order for some reason. It's not predictable. You can't assume anything about the order in which these key value pairs are going to be displayed. Then finally, on slide 34, we have UM1, our unordered map that we're constructing from the multimap MM1. And this contains the same pairs as the multimap, except that duplicate keys are not allowed. So in this case, when the key value pair O5 gets put into UM1 as part of its initialization, the later pair, little o9, is rejected. Likewise, L3 is inserted into the unordered map UM1, but the later occurrences of L with their values, namely little L4 and later little L1, are rejected. Okay, so that's a quick look at the 4 map container types. We've now looked at all 12 of those container types back in our table. The sequences, vector, dec, list, and forward list. The associative or tree containers, set, multiset, map, and multimap. And the unordered or hash table containers. Unordered set, unordered multiset, unordered map, and unordered multimap. Alright, next on slide 37, we're going to take a look at another batch of operations that are common to most of these standard container classes, namely equality, relational, and assignment operations. All of the container types can be compared to containers of the same type for equality and for inequality. That is, you can compare a vector of int to another vector of int. You can compare a forward list of char to another forward list of char. You can compare an unordered map from string to double to another unordered map from string to double, etc. For many of the standard container types, you can also do relational or ordering comparisons. That is, less than, greater than, less than or equal, greater than or equal. You can do these for all of the sequence types and for all of the associative or tree-based types, but you cannot do this, as I guess ought to be obvious from their names, for any of the unordered types. So unordered set, unordered multiset, etc. are not able to do any of these ordering relational tests. Assignment is available as long as the object on the left of the assignment is of the same container and element type as the value on the right hand of the assignment. And you can also, in C++11, directly assign to a container from an initialization list contained within curly braces. It's also possible to swap the values of objects back and forth, either using a swap member function or using a top-level function named swap that takes two containers as arguments. Okay, so we're going to take a look at this now, starting with this code on slide 38. And on slide 39, we have the output produced by the code on slide 38. All right, there's nothing really tricky going on here on slide 38. v3 is a vector of char initialized with 6 chars, H-E-L-L-O and an exclamation mark. v4 is also a vector of char initialized with 5 char, capital H this time, followed by lowercase e-l-l-o. And v5 and v6 are empty vectors of char. Now, we can test whether v3 is less than or equal to v4, and when you compare vectors, comparison is done on an element-by-element basis. So the first thing that happens here is that the element little h in v3 is compared to the element capital H in v4, and it turns out in the ASCII character set, as you may have memorized by now, that all capital letters have lower values than all lowercase letters. So our test for less than or equal to fails immediately. Little h is greater than capital H, and so the output produced here is false. Then in the next statement, we are testing whether v3 is greater than v4, and indeed it is. Again, we only have to compare the first char of each of these vectors to discover that little h has a greater value than capital H. So what's displayed there is true. Here we're doing assignment so that v5 now contains a copy of v4, capital H, little e-l-l-o. Here we're doing assignment of an initialization list, which is a nice thing to be able to do. And next we're swapping the contents of v5 and v6. So v5 used to contain hello with a capital H. v6 used to contain lowercase bye, but now their contents are swapped so that when we display v5 in this red range for loop, the output that we get is by, whereas when we display v6 in this blue range for loop, we get hello with a capital H as our output. So a couple of quick examples of relational tests, assignment, and swap. Here on slide 40, we have a table of which of these containers allow push and pop back, push and pop front, which allow subscripting with square brackets, which allow you to clear the contents of the container using the .clear member, and also which ones allow you to examine the front or back element using .back and .front. Most of these operations are restricted to the sequence containers, and whether they permit push or pop back and push or pop front has to do with what is efficient for these sequence containers. And by efficient, what we mean is that it's an order 1, that is a constant time operation. So we know that push back is efficient for vectors, decks, and lists, but not for forward lists. And it shouldn't be any big surprise that pop back, which takes the backmost element from the container, is also efficient for vector, deck, and list. Push front, on the other hand, is inefficient for vector, but it's efficient for deck, list, and forward list. Forward list is only efficiently modifiable at the front, whereas vector is only efficiently modifiable at the back. All right, and so pop front also is not provided for vector, but is provided for deck, list, and forward list. Now the back member function returns a reference to the element at the back of the container, and that's supported for the vector, deck, and list, but not for the forward list. If we wanted to get a reference to the back element of a forward list, we would have to write our own algorithm to traverse through all of the elements from the first element all the way to the last element, and then give a reference to that back element. Front, on the other hand, which also gives us a reference to an element, works for all of the sequence containers, vector, deck, list, and forward list. Now, as far as random access of elements using some kind of subscript, you can use square brackets for vector and deck, as we've talked about, but you cannot use square brackets for list or forward list. It turns out you can also use the square bracket notation for maps and unordered maps. The subscript is the key, and what you get by indexing using the key is the value associated with that key. Now, it's important to understand that the square bracket subscripting is not checked at runtime in the case of a vector or a deck. Checking at runtime takes a little bit of extra time, and C++ is severely allergic to taking a little bit of extra time, if that can possibly be avoided. So the square bracket is not runtime checked, and if you use an index that's outside of the range of subscripts for a vector or a deck, then what's going to happen is undefined. That could be any kind of behavior, from giving you back some kind of random value to crashing your program. If you want to do careful checking that the subscript that you're using is within the bounds of your vector or deck, then there's a .at member function that you give an index to, that is an integer subscript in the case of a vector or a deck, and that is checked at runtime. And in fact, if the index that you use is bogus, that is, it's outside of the range of values for a vector or deck, this will throw an exception which will crash your program. We will get into the details of exceptions and how you handle exceptions in Lecture 16. Subscripting for maps, it turns out, is different from subscripting in vectors and decks. You can use subscripting in a map and also in an unordered map. The index that you specify, if you use either the square brackets or the at member function, is the key. And if a pair with that key is found, what you'll get back is a reference to just the value part of the key value pair. Now, unlike vector and deck, where you get undefined behavior if you use an index that does not exist in the square bracket notation. In a map or unordered map, if you specify a key that does not exist within the container, what happens is it creates a new entry with the index that you specified as the key and the default value. Now that default value will be 0 for any of the built-in types, char, int, unsigned, long, double, and so forth. Or it will be whatever you get from the default constructor if the value is some kind of class type. For example, if the value is a string class object, then you will get an empty string as opposed to a string containing a 0 or something like that. As with vector and dec, if you use the at member function and you specify an index that does not match one of the existing keys in the container, this will throw an exception and crash your program. Notice that indexing or subscripting is not available for multimaps or for unordered multimaps. This is simply because the keys in a multimap or an unordered multimap are not unique, and therefore if you attempt to look up a particular pair using a key, it's not guaranteed that there will be either 0 or 1 value. Finally, clear is simply used to eliminate all of the elements of a container, and all dozen of the standard template library containers support clear. Here on slide 43, we have some examples with the output shown on slide 44. V7 on slide 43 is a vector of char, initialized with 6 chars. M2 is a map from a char for the key to an int for the value. And M2 is empty currently. If I say v7.front, what I get back is a reference to the first element in v7, and I can use that reference and assign a value to that referred to char. So what's going to happen here is that the little h will be replaced with little j. Following that, in this for loop, notice that I'm stepping through each of the elements in v7, one element at a time, and I'm using the ith element of v7 as my index into the map m2. Recall that going out of bounds on your indices in a vector would crash your program, but using a non-existent key as an index into a map will create a key value pair with the default for the value. So the first time through the loop, I is 0, v7 sub I is the little j that is now the first element in v7, and so when I say m2 sub little j, since m2 is empty, that's going to create a pair in m2 with a key of little j and a value of the default for int, so the value will be 0. Now what I'm going to get back from m2 sub j is a reference to that value component of the pair. And so into that value component of the pair, which is initially 0, I'm assigning some new value, specifically I times 2. Now here i's value is 0. 0 times 2 is 0, so I am assigning a 0 in place of the 0 that was already the value part of this pair. The second time through the loop, i's value will be 1. v7 sub 1 is little e. m2 sub little e doesn't exist, and consequently a pair with key little e and value 0 is created in m2. I get back a reference to the value part, whose current value is 0, but I'm assigning 1 times 2, which is 2, in place of that 0. So now I have an entry in M2 with a key of little e and a value of 2. The third time through the loop, i's value is 2. v7 sub 2 is little l. So I'm going to get an entry in M2 with little l as the key and 0 as the value. I get back a reference to that pair, and I'm assigning 2 times 2 is 4 in place of the initial 0 that value part had. Notice that the fourth time through the loop, i's value is 3, and v7 sub 3 is little l again. Now, because the little l key already exists in M2, this is not going to create a new pair. What I am going to get back is a reference to the value part of the pair whose key is little l. That value part currently contains a 4, that is the 2 times 2 that we stored in the previous iteration of the loop, but now I'm going to replace that 4 with a 6. So M2 sub little l is now 6. Then we store 8 into M2 sub little o, and 10 into M2 sub exclamation mark, and we're done with that loop. In this red range 4 loop, I'm simply printing out the elements of v7, which are JELLO exclamation mark. And then I'm using each element of v7 as an index or a key into my map M2. Okay, so this loop is going to run 6 times. The first time through, e is going to be set to little j, and I'll be told that M2 sub little j is 0. The next time, e is set to little e, and I'm told that M2 sub little e is 2. The third time, I'm told that M2 sub little l is 6. And because I have 2 little l's in v7, I also get a 6 when I look up M2 sub little l again. And then, of course, I get 8 for my key of little o and 10 for my key of exclamation mark. Continuing on, if I do an index of 22 into v7, the behavior of that is going to be undefined because 22 is well outside of the range from 0 to 5, which are the valid subscripts in v7. My program might crash, but let's pretend that it didn't. And I'm not seeing anything in the output, so perhaps that means that v7 sub 22 is accidentally a space character or accidentally a tab character, or perhaps it's a null character, and so I'm getting no output followed by a new line. On the other hand, if I use a non-existent key in M2, we know that what's going to happen there is that a pair will be created with key of little z and default value of 0. I'll get back a reference to that 0, and therefore 0 is what's going to be displayed on my screen. Finally, we have a couple of statements that are commented out showing that if you use the at member function on either a vector or a map with a bad index, that would throw an exception and crash the program. Here on slide 45, we've got a table showing various ways of obtaining iterators, marking the beginnings and ends of containers. We've been using begin to obtain an iterator for the first element of a container, and we've been using end as the iterator that is just past the end of the container. But there are also what are called reverse iterators and const iterators that you should be familiar with. So that's what we're going to be illustrating in the next few examples. So here on slide 47, we have an illustration of the difference between iterators and reverse iterators. Begin, as we know, here we're looking at a vector as an example, gives us back an iterator for the initial element in the container, and as we increment our iterator forward, eventually we will arrive at end, which is just beyond the final element of the container. A reverse iterator, on the other hand, when you use rbegin, gives you an iterator for the final element in the container, and perhaps weirdly, as you increment a reverse iterator, incrementing, that is plus-plussing a reverse iterator, moves backward until eventually you arrive at rend, the reverse end, which is just prior to the initial element of the container. Okay, so by using iterators between begin and end, that allows you to traverse forward through the container in whatever sense forward means, and using rbegin and rend, that allows you to traverse backward. Now, as you can see on slide 45, all of the different container types support forward iterators, starting from begin and going up through but not including end. For the unordered containers, reverse iteration doesn't really make any sense. An iterator from begin up to but not including end will go through each of the values contained in the unsorted container, but the order in which you receive those values is not defined, not predictable, and so the whole idea of going through this not predictable sequence in reverse is kind of nonsense, and consequently reverse iterators are not provided for the unordered containers. Likewise, reverse iterators are not provided for the forward list. In a forward list, you can only go forward. Here, starting on slide 48, we have some code illustrating forward and reverse iterators. The code is 3 slides long, and the output of the code is shown on slide 51. So let's walk through these examples and see how these forward and reverse iterators are working. We start out by creating V8, which is a vector of char containing 6 chars, HELLO exclamation mark. Then we use iterators on V8, v8.begin and v8.end, to create D3, which is a deck of char. LC2, on the other hand, is using reverse iterators, rbegin and rend. So whereas the D3 deck of char contains these 6 chars in the same order as V8, the list of chars, LC2, contains these characters in the reverse order that they're stored in D3. Just as a reminder of the awful actual syntax, if you want an iterator to traverse through your deck of char, the full type name of that is iterator that is a member of the deck of char class, and we're doing the usual thing here, stepping forward, starting from D3.begin, going up to but not including D3.end. So that's going to display HELLO, and in the red for loop, rather than typing out the full gory name of the iterator that is a member of the deck of char class, we just used auto. Now, for the list LC2, since we don't plan to change anything in the list, what we really should ask for is a const iterator. This is the equivalent for iterators of a pointer to const, if, say, you're using a pointer to const to step through elements of an array that you plan not to change. Okay, so it here is a const iterator that is a member of the list of care class. Therefore, we can access the thing that the iterator is pointing to with $it, as usual. But we could not modify the thing that it is pointing to by saying something like $it gets capital X. That would be a compile time error. Now, of course, we would really prefer not to have to type out that full obnoxious name, const iterator that is a member of the list of care class. We'd really rather just be able to use auto. But the problem here is that begin returns an iterator that is not a const iterator. So what we do here, because we do want a const iterator, is to use cBegin and cEnd. Okay? cBegin and cEnd yield const iterators, and so now we can use auto to say I want it to be initialized with lc2.cBegin, that is a const iterator that is, quote, pointing to, unquote, the initial element of this list. And then we go up to, but not including, the const iterator lc2.cEnd. Okay, now since lc2 was initialized using reverse iterators, remember we did rbegin through rend for initializing lc2, what's displayed from the first for loop on slide 49 is hello exclamation mark in reverse, and similarly in the red for loop we display the same thing. Now recall that we initialized the vector of care v8 with the 6 chars HELLO exclamation mark. v8 dot begin is going to give me an iterator for the initial element in v8, and I can say star of that iterator to give me access to that char that v8.begin, quote, points to, unquote, and I can assign a different char in place of that char element. Now, if I attempted to do this with cBegin, this would fail, because cBegin gives me back a const iterator, and I cannot modify what a const iterator is, quote, pointing to, unquote. Here on slide 50, we have a couple of for loops using reverse iterators to step through the elements of a couple of containers in reverse order. So we're initializing our iterator it with lc2.rbegin. That's going to be a, quote, pointer to, unquote, the little h that is at the end of lc2, and lc2.rend is going to be just prior to the exclamation mark at the beginning of lc2. So using reverse iterators, I can step through the elements in the list in reverse and display them, and what I get shouldn't be very surprising. It's the reverse of what I got when I displayed lc2 in forward order. Now, a tricky thing to understand here is that reverse iterators still make use of ++ to move to the next item in the list, but in this case the next item in the list is actually the previous item in the list. Alright, so this can be quite confusing, but remember that when you use reverse iterators, you still use ++ to go from one element to the next element. It's just that that next element is prior to the current element instead of after the current element. Similarly here in this red for loop, we're looking at the vector of care v8, and we're starting from its rbegin, which is the index of the exclamation mark at the end of v8, and we're stepping that iterator through until we get to the rend, which is just prior to the little j that is now the first char in the vector, And as I mentioned with LC2, we need to remember to use plus plus on our iterator to go from element to element, this time in reverse. So what we get when we display V8 in reverse is Jello exclamation mark in reverse order. So exclamation mark OLLEJ. Okay, so with these little examples, we've taken a look at iterators, we've taken a look at reverse iterators, we've taken a look at const iterators, and there are also reverse const iterators. So we can select the iterator that we want depending on whether we're moving forward through the container or backward through the container, and whether we want to treat the object that the iterator is, quote, pointing to, unquote, as a variable or as a const. Okay, so we can get iterators for containers using some form of begin or end, or rbegin or rend, or what have you. And we know that we can access the object that an iterator is currently, quote, pointing to, unquote, by doing star on the iterator. We know that we can move the iterator along to the next item by doing plus plus on the iterator. And we know that we can test whether an iterator is not equal to some other iterator, specifically not equal to end, by using exclamation mark equal. But now let's take a look at various other things that we can do to interact with and manipulate iterators as well. It turns out that iterators fall into three categories. There are what are called forward iterators that allow you to step through the elements of a container in one direction, whatever the natural direction is, for whether you use begin for an iterator or rbegin for a reverse iterator. There are also what are called bidirectional iterators, which allow you to go the opposite way of a forward iterator. So if you have a bidirectional iterator, you can go both forward and backward through the container. A random access iterator is able to go both forward through the container and backward through the container, and also do things like using subscripting to access a particular element somewhere in the midst of the container. Now, I want to be clear that these are categories, not data types. A forward iterator is an iterator that provides certain operations that allow you to move the iterator forward through the container. A bidirectional iterator allows you to not only move forward through the container, but also to move backward through the container. And a random access iterator is an iterator that allows you not only to move forward and backward, but also allows you to access arbitrary elements using subscripts. You can also do things like comparing whether one random access iterator is less than another one, and so on. So specifically, an iterator is a forward iterator if it supports all of these operations. That is, it needs to be able to support star to access the element of the container that the iterator is currently pointing to. It also needs to support the arrow notation in case the iterator is pointing to a class or a struct that has member functions or data members. It needs to support the plus plus operation, which will move the iterator forward to the next element in the container. And not only must it support the pre-increment, but it must also support the post-increment. Now, the post-increment, it turns out, is less efficient than the pre-increment, and so the post-increment is very seldom used. A forward iterator also needs to support equality testing, also inequality testing, and assignment of an iterator to another iterator of the same type. Taking a look at this table on slide 52, we see that all dozen of these container types support forward iterators. That is, they support all of the necessary operations shown for forward iterators here on slide 53. Let me clean up this blast of highlighting that I just did. As a special case, the maps, map and multimap, unordered map and unordered multimap, since these containers contain pairs, then any iterator that you have will be able to access the first element of the pair, which is the key, and the second element of the pair, which is the value. Now, bidirectional iterators have to support decrementing an iterator, that is, both pre-decrement and post-decrement of the iterator. You can't do decrementing of a forward list iterator, and likewise you should assume that you can't do decrementing of an unordered containers iterator. Implementations are apparently allowed to support decrement for unordered containers, but since it's not a requirement, you're much better off assuming that that's not available. And then finally, random access iterators support subscript, as we've seen. You can also subtract one iterator from another to find out how many elements exist between those two iterators. You can add arbitrary integers or subtract arbitrary integers. You can do plus gets and minus gets. And you can do relational comparisons on these iterators, more or less as though these iterators really were pointers. Now, among these dozen container types in the standard library, the only ones that support random access iterators are vector and dec. You can add or subtract integer offsets from vector and dec iterators. You can use subscripting and subtraction on vector and dec iterators. And you can do relational comparisons of vector and dec iterators. But none of these other 10 standard container types support the random access facilities. Here on slide 54, we point out again something that I said before, which is that the pre-increment and pre-decrement operators on iterators are more efficient than the post-increment and post-decrement. So you should get in the habit of preferring pre-increment in things like for loops rather than post-increment in the change expression. Why is there this efficiency difference? Well, in a pre-increment, the increment happens first and then you use the modified value afterwards. So you only have to have one object sitting around. You add to it and then you use it. In post-increment, though, remember that the incrementing only happens after you make use of the value. So you have this odd thing going on in post-increment that you have to sort of make this temporary copy of what the original iterator was, and then you increment the underlying actual iterator. So this doesn't look like a big deal, but it does entail actually creating a copy of an iterator, and unless you have some specific reason for needing that copy, it's better to just not waste the time. Another thing I want to point out, particularly with regard to random access iterators, is that you need to be careful not to go ahead of the begin iterator or past the end iterator. In this example for loop, I'm using an iterator to step through the elements of a vector. We know that a vector has a random access iterator, therefore we could compare whether our iterator is less than v9.end, which makes this look even more like a typical kind of for loop that we would use with an integer subscript or with a pointer. The problem here is, if I do something like adding 2 to my iterator, that's permitted because the iterator is a random access iterator, but what if adding 2 to my iterator jumps past v9.end? Is v9.end plus 1 going to be greater than v9.end? Well, once you're outside the bounds from .begin through .end, all bets are off. It's undefined whether the value of v9.end plus 1 is greater than or equal to or less than v9.end. So you could accidentally create for yourself here an infinite loop, or you could crash. Here on slide 56, we have some examples of using the random access iterator that you get with a vector. And on slide 57, we have the output of this little bit of code. So v10 here is a vector of int. It happens to contain 10 values, 13579, A6420. And here we're declaring it as an iterator initialized to point to the beginning, that is to the initial element of that vector v10. Now, because random access iterators allow me to do subtraction, and when I do a subtraction, what I get is the number of elements between the two iterators. If I subtract from v10.end, this iterator, which currently is v10.begin, what I'll be told is that there are 10 elements between the end and the beginning. Recall that end is just beyond the final value of the vector, so if we were thinking of this in terms of integer subscripts, this would be the equivalent of subtracting a subscript of 0 from a subscript of 10, which is one too far. I can access the element that IT is pointing to. At this moment, that's the initial element in the vector, which of course is 1. Now, if I add 3 to my iterator, since this is a random access iterator, it behaves properly and simply shifts the iterator forward by 3 positions, so that now, if I use my subscript notation on the iterator, this is a bit like using a subscript on a pointer. The iterator is, quote, pointing at, unquote, the 7, so IT sub 0 at this point is 7. I can use negative subscripts, just as I could if IT were an array or a pointer. IT sub minus 2 is the element that is 2 before the 7, which is going to be the 3. And if I set my iterator to the end minus 4, well, the end is going to be just beyond the 0, so minus 1, 2, 3, 4. The end minus 4 is going to be pointing at the 6. Okay, so the subscripting, the subtracting, the plus gets, these are things that random access iterators can do that forward iterators and bidirectional iterators are not able to do. Okay, here in this table on slide 59, we're showing how to assign collections of values to a container, which will also have the effect of eliminating all of the values that the container used to contain. We're seeing how to insert a value or a collection of values into a container, which may move around but otherwise will leave unchanged the values that currently exist in the container. We can erase individual values or sets of values specified by iterators, and we can also remove all occurrences of some value, or in the case of removeIf, all of the values that satisfy some Boolean operand. Now, as you can see, not all containers support all of these capabilities. And some of the containers support some of these capabilities in a slightly modified way. Let's take a look at what this asterisk is about on slide 60. Okay, first of all, notice all the asterisks that we've got here on these forward list operations. In a forward list, you only have forward iterators, so you cannot, for example, move to a particular element in the forward list and then insert a new value ahead of that existing value. If you have an iterator for an element in the forward list, then in order to insert a new value there would entail modifying the previous element in the forward list, and that would require going backwards, which you cannot do. So for the forward list, instead of insert and erase, we have insert after and erase after. Also, for all the associative containers and the hash table containers, what the asterisks here on all these yeses imply is that you do not specify a position that is an iterator where the insertion is supposed to occur, because the associative containers and the unordered containers maintain their own internal structure about where things are supposed to go. So you can insert a value without specifying where that value is supposed to go, and so forth. Also, just as a matter of historical inconsistency, whereas we would use remove to remove a value from a list or a forward list, it turns out we use erase instead of remove for the associative containers and the unordered containers. A lot of effort has been put into trying to keep these interfaces and member functions as similar as possible, but here we've fallen short of perfect. On slides 61 and 62, we have example code making use of the assign, insert, remove, and erase facilities. And then on slide 63, we have the output produced by that code on slides 61 and 62. So let's walk through this example. Here we have a vector of int v11 initialized with 135, and then in place of the original contents of v11, I'm going to assign new contents. Notice that this version of assign takes an initialization list, that is, a sequence of values contained in curly braces and separated with commas. So after this assign, v11 will contain that sequence of 11 int values. Into the list of int li1, as initial values, I'm providing a subrange from v11. Since a vector of int has random access iterators, I can use addition and subtraction of ints with my iterators. v11.begin plus 1 is going to be an iterator 1 past the initial element of v11, so that's going to be an iterator for the 2. And v11.end minus 1 is going to be an iterator for the 6. That is, for the last element in v11. Now recall that if I construct a container specifying a beginning iterator and an ending iterator, then everything from the beginning iterator up to but not including the ending iterator is included. So in this case, what's going to be included is everything from the 2 up to but not including the 6. All right? Here in this black range for loop, I'm displaying v11. That's this first line of output. And then in this blue range for loop immediately below it, we're displaying the contents of li1, which is this subrange of what's in v11. Remove for a list or for a forward list can be given a value as an argument, and the list will be traversed. Any occurrences of that value will be removed from the list. So in the case of li1, these 3 zeros are going to be removed from the list. So the list contains 2, 4, 6, 8, 2, 4. Notice here I'm declaring an iterator, it2, initialized with li1.begin. Now a list does not have random access iterators, but it does have forward iterators, and so I can increment my iterator once and twice to move the iterator ahead 2 positions. Okay, so when the iterator was at begin, the iterator was at the 2, and when I move it forward 2 positions, the iterator is, quote, pointing at, unquote, the 6. Consequently, when I say li1.erase whatever is at that iterator it2, that's going to erase the 6. And so now, in this red range for loop, when I display the contents of li1, I'm going to just have 24824. That is, the 3 zeros were removed by the remove member function, and the 6 was removed by the erase member function after I had started my iterator at the beginning and incremented forward 2 times. The next thing I'm doing here is I'm inserting into v11, starting at the location v11.begin plus 2, that is, v11 contains 0, 2, 4, 6, 8. v11.begin plus 2 is therefore, quote, pointing at, unquote, the 4. So I'm inserting ahead of the 4 the entire contents of li1. That is, everything from li1.begin up to but not including li1.end. And sure enough, we see here the values in li1 inserted ahead of the 4. so that when I display vi11 in this green range for loop, I get out vi11 modified with the contents of li1 inserted ahead of the first 4. Finally, here on slide 62, I'm creating a multiset of int msi. Initially, msi is empty. Then I'm doing an insert into msi, the entire sequence of values in the vector v11, from the beginning up to but not including the end. When I display msi in this black range for loop, the elements of msi are the same as the elements of v11, except that a set, in this case a multiset, stores elements by default in ascending order. So I have 4 zeros, 4 2s, 4 4s, 2 6s, and 2 8s. Now, if I, from MSI, erase 0 and erase 6, that's going to erase all the zeros and all the 6s from MSI. So when I display MSI again in this blue range for loop, the 4 zeros and the 2 6s have in fact been erased. Into MSI I can insert a specific collection of values by using the initialization list notation. Here I'm inserting 5 negative integer values. And I can also insert one value. Here I'm inserting a 7. So now when I use yet another range for loop to display MSI again, what I see is that all of the negative values have ended up in ascending order ahead of the positive 2, and the 7 has been correctly inserted between the 4 and the 8. So I still have this collection of values in ascending order. Finally, di here is a deck of int. Notice that I'm initializing di by using reverse iterators on MSI. So what's going to go into the deck di is all the values in MSI starting from the reverse beginning, that is, starting from the last value stored in MSI, to but not including the reverse end. And recall that the reverse end is just prior to the first element in MSI. So if we look at the display of di produced by this green range for loop, you'll see that it has exactly the same values as MSI in exactly the reverse order. So how to summarize? This seems like just a giant catalog of stuff. It's a bit hard to get a handle on all of it, but it's extraordinarily important to try to get a handle on as much of it as you can, because what the standard library containers and iterators provide is virtually all of the standard data structures used in applications, with mechanisms for initializing, modifying, erasing from, and traversing through the contents of all of these data structures. These are extremely useful examples of what's called generic programming. All of these containers are generic. They can contain any kind of copyable data. The iterators are generic. They can be used to, quote, point to, unquote, any type of element that can go into one of the containers. And when we combine these things with algorithms, you'll see that we have tremendous power to store and manipulate almost any kind of data in almost any way that you can think of.